Hi, my name's Alissa Schembor.
I'm Anthony Petrosino.
We're from Villanova University, and the topic of our research discussion today is tiling, enumeration, and profiles. So our original question that we began our research project with was to understand how many different ways there are to tile a rectangular n by n board using squares, dominoes, and trominoes. And so in the example below, it's a 3x4 board, and it uses a variety of squares, dominoes, and trominoes. And so while we were working on our research projects, we referenced two former research projects that involved the tiling of a 2x n and a 3x n board. And by understanding these research projects, we were able to use profiles, which are the different edges of partial tilings. And we can see a profile shown below. And these profiles can be represented by strings of numbers. So this profile below would be a 2, 0, 1 string. The goal of our talk today is to explain how the number of profile type strings can be represented by the formula m times 3 to the m minus 1, where m is the number of rows in an m by n rectangular array. So target squares are a key concept that we had to begin our research project with. And so in order to create different profiles, we begin by placing a square, domino, or a tromino onto the target square. And the target square is the leftmost, topmost unfilled square. And so in the example below, it is denoted by the X. And so in order to find the target square, you must find the topmost uncovered square in the leftmost column with an uncovered square, and that's where we place the X. So profiles are the outline of the right-hand side of a partially tiled board, and we can see a profile below. And these profiles can be represented by strings. So the profile below would be a 2, 0, 1 string. And so for each profile, we're going to assign them a string length of m, which can be 0, 1, 2, or 3. And these are going to denote the number of tiled squares in each of the rows beyond the leftmost fully tiled column in the profile. So in the example below, there are two fully tiled columns to the left, which is why our profile is 2, 0, 1 rather than 4, 2, 3. So an example of tiling for us is going to be a 3x4 board, and is going to start blank, meaning that the target square is going to be in the leftmost topmost region, which is where the X is right now. And this profile string is a 0, 0, 0. Next, we are going to place a vertical domino. And so this causes the target square to move down to the last row. And our string would be 1, 1, 0, because there's one item in the top row, one item in the middle row, and 0 items in the bottom row. Next, we place a tromino horizontally, and this causes the target square to move back up into the first row. And this profile string would be considered a 0, 0, 2 profile string. Next is we added another tromino horizontally, and this causes the target square to move down into the middle row, because that is now the leftmost, topmost untiled square. And so this profile string is going to be a 3, 0, 2. And although it may appear to be a 4, 1, 3, we have to remember that profiles are denoted by the number of tiled squares that are beyond the leftmost fully tiled column. And there's one fully tiled column, meaning that our profile string is now 3, 0, 2. So next we added a square, which caused our target square to move to the right by 1, and this is denoted as a profile string of 2, 0, 1. And next we added a horizontal domino, so this caused our profile string to be a 1, 1, 0, and our target square is now moved into the final untiled region of the 3x4 board. And then finally, we place a square into the remaining untiled region, and this is going to cause us to have a board or a profile string that is 0, 0, 0, which is exactly the same way that we started. And so for our different profiles, we were able to find that in the 2x n case, there were 6 different profiles. In the 3x n case, there were 27 different profiles. But our question arose of what happens for the 4x n case and beyond. And this is where we had to create a formula in order to understand what happens in the larger cases.
Yeah, so one way to study this is by using profile type strings, and profile type strings are basically just a way to represent profiles numerically so that we can study them at larger and larger amounts of rows. So we attached a couple rules to profile type strings. The first being that there has to be a 0 somewhere in the profile type string, otherwise there wouldn't be a target square. And the second rule is that after a 0, there cannot be a 3. So some examples of profile type strings: 101 would be a valid profile type string because there's a 0 in the string and there's no 3 after the 0. 213 would not be a valid profile type string because there is no 0 in the string. And 013 would also not be a valid profile type string because there's a 3 after the 0. So this led us to a couple of propositions and a theorem. The two propositions being that there's 108 profile type strings for the m equals 4 case, which means that for 4 by n arrays, there's 108 profile type strings. And then there's 108 profiles for the 4 by n case. And the profile type strings and the profiles, we think that they're one-to-one, but we have not proved that yet. But this led us to the theorem about the equation that says that the number of profile type strings is equal to m times 3 to the m minus 1, where m is the amount of rows in the array. So how do we prove this? Well, we're basically going to set up a bunch of zeros throughout the profile type strings and see what happens after. So if we put the 0 in the first spot, every entry after that only has 3 options, which is 0, 1, or 2. And if we put the 0 in the second spot, then every spot before that, which in this case is just x1, can be either 1, 2, or 3. And then every spot after that, it can either be 0, 1, or 2 because you can't place a 3 after a 0. So if we generalize this, every 0 that we place throughout the array, every spot before it has 3 options, which is either 1, 2, or 3. And every spot after it has 3 options, which is either 0, 1, or 2. So there's m of these cases because we're going from x1 to xm, depending on the amount of rows. And each of these cases has 3 to the m minus 1 strings. So if we put those two together, then it's m times 3 to the m minus 1 strings. And this led us to the conjecture, like I said before, that the profiles are in a one-to-one correspondence with the profile type strings. If this were to be true, we'd be able to study the profiles by just using the profile type strings, which would make it easier because we know certain rules about those now, and we can study them numerically. And proving this conjecture we're still going to collaborate for the rest of our time and try to work on this. So. And so thank you to Richard, Phil, and Jerry for help with programming for counting profiles, and thank you to the rest of the acknowledgements.